Alright guys, so what we talked about today in class was more or less just introducing this concept of static equilibrium. So we talked about just kind of some intuitive understanding of how that works in bridges and trusses and other structures. But what we really need to take from this is that an object that's in static equilibrium, we know two things about it. We know that because it's not moving, because it's not going anywhere, the sum of the forces in the x are going to be equal to 0, meaning that for every force applied in the x direction in one way, there are equal and opposite reaction forces that essentially are just going to push back with the same amount of force that's going to keep that stationary. All right. Same deal with the forces in the y direction. So the sum of the forces in the y direction are going to be equal to 0, and it's the same type of deal. If we have something pushing up on an object and that object is not moving, we know that the reaction forces have to be equal and opposite, so that we have equal and opposite forces pushing back at that object. All right, so what we want to do is we want to take a look at an example problem here. So our example is an object that weighs 1,200 pounds. Is suspended from two cables. The first of the two cables forms a 60-degree angle with the ceiling. The second cable forms a 45-degree angle with the ceiling. Find the tension in pounds of force. And we talked about that tension is a particular type of force. But we want to find the tension on the cables. All right. First thing you want to do is draw yourself a picture of what's going on. And I've started that real quick. So down here we've got the first force, which I labeled F sub 1, is this guy right here. There's another force on the cable over here. So this is my first cable. This is my second cable. And we know, again, with those cables, the first cable forms a 60-degree angle with the ceiling. The second cable forms a 45-degree angle with the ceiling. And the last thing that we know then is that the object weighs 1,200 pounds. And the way that we're going to kind of display this is we're going to draw a vector here that I'll name F3. This is the force vector for the object. All right, and we know that gravity pulls down and applies a certain amount of force, and in this case it applies 1,200 pounds of force on this particular object. All right, so what we want to do is we have our three forces, and so we've got what we want to do is write these as force vectors and then use these laws that we kind of established on the last slide here. We know that the sum of the forces in the x is going to be equal to 0. The sum of the forces in the y is going to be equal to 0. So we want to use those laws of statics in order to figure out what's really going on here. Okay? Each one of these forces has an x component and a y component. This guy, just generally, we know that the force is going to be applied in this direction. This force is going to be applied in this direction. This force is downward. So for F1, in order to write the force vector for that thing, we know that we have to take the magnitude of that particular vector and multiply it by our two components. So the first thing is the magnitude. We don't know what the magnitude is, so I'm just going to use A to represent that amount. And I'm going to multiply that by the first component is cosine of whatever the angle is. And in this particular case, the angle is going to be this angle right here. So here's my vector. Oops, that's the wrong color. Let's get rid of that. Here's my vector right here. Here's the x-axis. This is the angle that we're actually interested in. And so we know that if we just drop a line straight down, if this is 60, this has got to be 30 because that's a right angle. So 90 and 30 is 120. So the cosine of 120 degrees is going to be the reference angle for this particular vector, the direction of this particular vector, I should say. And then that's the I component. And then the J component is going to be the sine of that angle. So the sine of 120. And my force vector looks like this. A cosine of 120 plus a sine of 120. All right, so there's my first force vector. So let's just kind of highlight that. Maybe I'll underline it. We can come back to it later. Second force vector then. Let's do a little different color here. Second force vector is going to be this guy right here, F2. All right, this is 45 degrees. If we drew a horizontal line, a couple different ways you can do this, but if we drew a horizontal line, we know that this is going to be alternate interior. So this angle right there is the direction of my vector. That's what we're interested in. But these are alternate interior, so I know that my reference angle or my direction is going to be 45 degrees. So let's go down and write that second cable. We want to write the tension on that second cable as a force vector. So this is going to have a different magnitude. We can see it's a little bit longer. So the magnitude we would expect to be a little bit greater. So we're going to call that one B. And again, just write our different components. Cosine of 45. I plus cosine. Oops, sorry. Plus sine of 45J. Go through and simplify, and we'll expand this out. And we've got our second vector. And this is going to represent the tension or the amount of force on the cable. So we've got B cosine of 45 I. There's my x component plus B sine of 45J. All right, so we've got these two vectors. Those are the vectors that are representing the forces on the cables. And the last one that we have to deal with is this vector down here, the one that represents the weight that's pulling downward, or really the force of gravity is what creates this this force. So what we want to do, again, we've got to do the same thing. We've got to write this as a force vector, and we're going to call that F3. And this one should be an easy one. We know the magnitude of this thing. If we're going to go through the actual entire process, the magnitude is going to be 1200. This vector is pointing straight down, so I would do a direction of 270. So if I'm going to go through this entire process, it would be 1200 times cosine of 270. That's my I component, plus sine of 270. That's my J component. And if I went through and simplified, we're going to plug this into the calculator. What actually ends up happening, and this makes perfect sense, this vector is not applying any force in the x direction. So we know that the cosine of 270 is 0. Multiply that by 1200 and we get 0I. So it has no I component. It has no force in the x direction. The sine of 270, however, is 1. Okay? So it would be 1200 times 1, which just gives us 1200J. And it makes perfect sense. We've got this this object is being pulled down by gravity, which means all of this force is being applied in the y direction. So my y component should be 1200 and my x component should be 0. All right, guys, so what we want to do is a little bit of simplification based on what we know, particularly about 30, 60, 90 triangles and 45, 45, 45, 90. I'm sorry, 45, 45, 90 triangles. So what we want to do is just draw a little diagram. I want to show you what's going on. So I've got this 30, 60, 90 triangle, and this is with reference to the first cable here, the force on the first cable. I know that in a 30, 60, 90 triangle, the first part here, cosine, is going to relate the distance in the x direction. And we look back up at our diagram, and we know that this piece right here and this piece right here are going to be exactly the same. And in a 30, 60, 90 triangle, if we label that x, well, the cosine function relates this distance to the hypotenuse. And the hypotenuse in a 30, 60, 90, if this distance is x, the hypotenuse is 2x. The last piece of this then is to understand that we're dealing with a 120-degree reference angle here, or direction of this vector. And so we are traveling in the x direction, in the negative x direction. So if we're going to simplify this cosine of 120, we know that it has to be negative x. We're going in the negative x direction. The hypotenuse is still 0, so the cosine function for this particular thing is going to relate the adjacent side to the hypotenuse. And if you simplify that, it's negative x over 2x. The cosine function of this particular angle is going to be negative 1/2. All right. So for this particular thing, we know that we can simplify this this force vector by saying, hey, we know some stuff about 30, 60, 90 triangles, so I know that this is going to simplify to negative a over 2I, and then the sine of 120. The sine of 120 is going to take this particular distance right here. It's going to relate the opposite to the hypotenuse. This distance right here we know is root 3, or x root 3 in this particular case, and then the ratio reduces to root 3 over 2, and that's positive. So we've got negative a over 2I, and then positive root 3 over 2j. Okay, so here's our force vector for the first cable. Second cable, we can do very similar things, and let me drag that down real quick, and we'll go through this one a little bit quicker. But for the second cable, we've got these particular values. So we want a cosine of 45. If I draw my 45-degree triangle here, I know the cosine is going to relate the x direction. And so if this is x, then this is x, and this is x root 2. So we can write our ratios using that. So this is going to end up being the force on the cable, on the second cable, is B. Cosine of 45 is x over x root 2. So root 2 over 2 if we rationalize. That's the I component. Plus the j component is also going to be root 2 over 2. So we're going to have B root 2 over 2j. All right, guys, so the last piece of this is we want to draw in what we talked about earlier with these equations of static equilibrium. If this thing's not moving, then we know that the sum of the forces in the x, for every force in the x direction, there's going to be an equal and opposite in the opposite x direction. And so the sum of all of our forces in the x direction are going to be 0, and the same thing for the y's. Any force that is acting in the y direction, there's an equal and opposite force in the opposite direction. All right, so let's go ahead and see how that applies to our particular example. So what we have, again, the sum of the forces in the x are going to be equal to 0. And where are my forces in the x direction? Well, here's one. And here's another. So those are the forces in the x direction for my two tension cables. And for this guy up here, the object, the gravity pulling down on the object, well, there's no force in the x direction. So when we combine these, we know that the sum of these is going to be equal to 0. And go through and solve. Essentially what we're trying to do is solve for a and b. All right, so we're going to end up with an expression for a in terms of b, or vice versa. And what we can do is we can just eliminate these i's. These are just the components that indicate that these go in the x direction. So I'm going to simplify this a little bit. Hopefully you see where these two pieces come from. But here's my expression. It's equal to 0. Go through and multiply by 2, and you get negative a. And then we can move this over to the other side, and we get minus b root 2. Or a equals b root 2. So there's one expression. All right, we're going to come back up. We're going to look at the sum of the forces in the y direction. And again, those are our j components from each one of these. All right, so let's go ahead and pull what we need here. Here's one. That's from the first tension cable. Here's the second one. And here's the third one. All right, so I recognize one little mistake here as we go back. We went through and we know the cosine of 270 is going to be 0, and that's going to cancel out our I component. But the sine of 270 is actually negative 1. And when we multiply that by the magnitude, it should give us a negative force for this, basically the force of gravity acting on this object. So that now makes sense because that would help us to balance our equation. So that would make us negative. And we go ahead and we are adding these two components together. That'll be equal to 0. Again, we can drop the j's because that's just indicative of these forces acting in the y direction. So we've got a root 3 over 2 plus b root 2 over 2, and we can move that over, set it equal to 1200. All right, so simplifying, we want to multiply by 2. We've got a root 3 plus b root 2 equals 2400. So now if you see this, what we've got are two expressions. We've got an expression for a. In terms of b, we've got another expression in terms of a and b, and this is essentially just a system of equations. So our expression for a, we can go over and plug in for a over here. So plug, and what we end up with is b root 2 times root 3 plus b root 2 equals 2400. B root 6 plus b root 2, we can actually factor out a b root 2 out of this. And b equals 2400 over root 2, root 3 plus 1. Not really essential that you factor this out. We do need to factor out the b so that we can move this expression over. So what we ultimately want to do is find that decimal, or in this case the amount of force or the magnitude of the force on that second cable there. All right, so plug that into your calculator. I'll go ahead and do that now. And what I end up with is 621.17, and that is pounds of force. All right, so 621.17. Go over and plug this in for b over into this equation, and we'll get a equals 621.17 times root 2. So a is about 878.46 pounds. So there is the amount of force applied to the first cable. There's the amount of force applied to the second cable. Let's go up and make sure we've answered our questions, and we have.